Good morning all. Today's topic will discuss about the constraint satisfaction problem. So we call CSP. So you know what is meant by constraint? Constraint is some limitation, some conditions, some restrictions. Right? So constraint is nothing but where depending upon some of the conditions or the limitations, the solution is going to be formed. So now an agent is going to find a solution using CSP, right? So it is constraint satisfaction problem, right? So it is going to consist of three things which you have to know before arriving this constraint, right? So constraint is nothing but some limitations in order to find the solutions or to reach your goal. So it consists of three main things where you have to define first about the variables, right? So which is going to store the solution. So solution can be in the form of a value. So to store the value we need some variable, right? So it is going to be a finite set of variables, so which is going to store the value and it is defined with V, right? And second, we have a set of discrete values known as domain. So what is domain is from which the solution is going to be found. That is going to be called as a domain, which is defined with D, right? So finally, a set of constraint. So there is going to be a set of constraint for each problem. Based on the constraint, we are going to derive the solution from the given set of domains. All the value is going to be defined in the form of sets, right? Right, so how we are going to convert the given problem into CSP? First step, as I said, you have to create a variable set based upon what problem you are going to solve it. Second, you have to create the domain set, and third, you have to create your constraint, right? So constraint, and you have to define what are the possible constraints based upon the solutions, you have to derive it. And finally, you have to find the optimal solution, right? So that is your constraint satisfaction problem. So this is a real-time example. If you see, everybody will play this Sudoku, right? So Sudoku is where there is going to be a 9 cross 9 matrix format, which will be in the form of a grid, where you have to find the solution. The value is filled between 1 to 9, right? And here we have a constraint, right? You can't go and simply fill the 9 values in each the grid, right? So you have to have a constraint where the solution is going to be derived that no number should be same on the same row and in the same column. That is the constraint we have to follow, right, in order to find the solution for Sudoku. So here the variable is going to be nothing but the boxes where each boxes is going to hold a value. So we have to define a variable for it. So this is 1 cross 1, 1 cross 2, 1 cross 3, right? So it will be in the form of a matrix, right, in the form of a grid. And domain is nothing but a value. The solution is you have to fill the Sudoku with the number from 1 to 9, right? And what is the constraint is no number should be on the same row and same column. So this is the real-time example which the constraint satisfaction problem helps in finding the solution. So for finding the constraint satisfaction problem, we have to define three things, right? So one is variable, one is domain, one is constraint. So here variable, as I said, which holds the value, which is nothing but the boxes. And what is the domain is where it finds the solution, right? So from the given range of value from 1 to 9. And what is the constraint is, as I said, the game rule is no row, no number should be on the same row and same column, right? So this is a real-time example. But when we come here to the constraint satisfaction problem, mainly we'll discuss about the graph coloring problem or map coloring problem. I hope in design and analysis of algorithm you could have studied about graph coloring problem. So what you've done in the graph coloring problem? In graph coloring problem, no adjacent node should have the same color, right? So that is where the constraint, based on the constraint, you have derived the possible solution. In that you have find which is your optimal solution, right? So same thing, right? So we will discuss about the map coloring problem, right? So consider this map. So where this is a map where it has Western Australia, Northern Territory, South Australia, Queensland, New South Wales, Victoria and Tasmania, right? So these are the maps. So the map is given, right? So what is the value which is given for the domain is only 3 values which is given, where you have to fill the map with 3 colors which is given as blue, green and red. Right? So there are 3 colors which is called as domain values. You have to fill the given map with the colors. Now what is the constraint? Constraint is no 2 adjacent should have same color. When I fill the color in Western Australia with red, I cannot fill red with Northern Territory and South Australia. So that is the constraint. So with the help of the constraint, you have to color the complete map. So as here the Tasmania is separate from the map, we don't have issue of filling of any 3 colors or possibles. Correct? Because that is not adjacent with any of the nodes. Right? So what is the domain variable in this is where the name of the countries is being given here. Right? So you can write the Western Australia as WA, Northern Territory as NT, South Australia as SA, and Queens Island as Q, and New South Wales as N as W, and Victoria B, and Tasmania T. So these are your variable. What is domain value? Domain value is blue, green and red. And what is the constraint in this? Constraint is no 2 adjacent should have same color. Right. So now if you observe first in this graph, so first let us take Australia, Western Australia. You can, since this is the first node, right? So in the map, this is the first part. So you can fill the map with either by blue or green or red, right? Anything is possible. Suppose if I fill the map with red color. So this is with red. I am filling this with red. So if it is filled with red, the adjacent should not have the same color. So I can't fill red and red here, right? So from the domain value we have filled red. Now what is the possibility of the next node, Northern Territory, can be filled? So as the red is over, either you can fill with the blue or you can fill with the green. Yes or no? Right? So I am filling the Northern Territory with green. Suppose this is, I am filling this with the green. If I fill that with the green, right? And what about South Australia? South Australia I can't fill with green and I can't fill with the red because that is adjacent of Northern Territory and Western Australia. So I can't use the same color which is green because it will violate the constraint. Right? So I have to stick with the constraint, from that only the possible solution, and that which is going to be optimal solution we have to derive. Right? So that is your constraint satisfaction problem. So now since I used these 2 colors, right, my only option for this is only blue I can be used. So I can fill this South Australia with blue. Right? So I have filled it. Right. So now what about this Queensland? Queensland, where it is adjacent of Northern Territory and South Australia. But Northern Territory and South Australia is already filled with green and blue. So I can't fill this Queens Island with the green and blue. So what is the only possibility? Only possibility of filling the Queensland is with red. Because red is, which is given for the Western Australia, is not adjacent to the Queensland. Right? So we can provide red over there. Right? Now coming to the New South Wales. So New South Wales is adjacent to Queensland and South Australia. So already red is being given for the Queensland, which I can use for New South Wales. And blue is already given for South Australia, which I cannot use for New South Wales. So what is the only option which I can give for the New South Wales is the green color. So I can fill this with the green color. Right. Now coming to the Victoria. So Victoria, which color I can be filled? Victoria is adjacent of New South Wales and South Australia. Those 2 are adjacent. So those 2 already have a blue and a green color. Right. So what is the only possibility? The remaining color what we have is red. So I can fill the Victoria with red. Right. So now coming to Tasmania. Tasmania is complete separate from the given map. So you can fill the color with either red, or you can fill the color with either blue, or you can fill the color with either green, because that is not adjacent to any of the node. Right. So as it is not adjacent, you can fill any one of the color. So this is where you can fill the map coloring problem from the given constraint, right? Right. So if you observe the variables which is defined, this is where I discussed about the variables which is defined, and the domain value is where the three colors of red, green, blue, and constraint is, as I said, no adjacent region should have same color, which means that they should have different colors, right? So this is where we done, right? So this is one solution, which doesn't mean that this is the only solution for the map coloring problem. As I started with the Western Australia as red, we have got the solution in this way. If I start Western Australia with green, I will get different solution. If I start Western Australia with blue, I will get different solutions, right? So we can get a multiple possible solutions in the map coloring problem, right? So this is one of the solution which satisfies all the constraints what we discussed in the graph coloring problem, map coloring problem, right? So now coming to the values which is assigned to the variable, right? So it is going to be defined with the variable which is equal to value, right? And x of I is equal to v of I is where the value of a variable which holds the value v, right? So x is a variable which is assigned with the value of v. So like that we will have the multiple variables and values, right? So a state is an assignment of a values to all the variables. So while assigning the values, we have some constraint in that. There are many types in that type of assignments of a value. One is legal assignment, one is partial assignment, and one is complete assignment. So what is meant by legal assignment? Legal assignment means when it satisfies the constraint, right? So whatever a problem has, we have a constraint to reach the solution. So those constraints, if it is being satisfied, then it is a legal assignment. So what is mean by partial assignment means value has been assigned, but for few variable there may not be a value, right? So where we call it as partial. What is mean by complete assignment? Complete assignment, all the variable definitely will have a value, right? So based on these types of assignments only, we will assign the value to the variable, right? So this is talking about the definition, what we discussed about the legal assignment, complete assignment, and partial assignment, right? So what is the solution to the constraint satisfaction problem? It should be always complete and consistent assignment should be available, right? So then only we can achieve the objective function, maybe the maximization of the objective function can be achieved when we follow the complete and the consistent assignment, right? So in order to make it precise, we will convert the given graph into given map into a graph. So we know that the graph will have node and edges. So it is easy for us to understand which region has the more constraints on that, so that we can easily find out the solution, right? So manually, by seeing that, we have colored the map, right, based on the constraints. But how the system going to understand and do it, right? So we can convert the given constraint map coloring into a constraint graph, right? And it is easy for visualization, right? So and it is going to have a nodes, right? So which is correspond to the variable what we are using it. If you take here the Southern Australia is SA, right? So Western Territory is your WT. So like that is going to be represented in the form of a node. and the links connecting any two variables is going to be talking about the constraint what exists between those regions, right? So if you observe here, this is your constraint graph from the given, right? So in this, the southern Australia is where it has more constraint because this is adjacent to the Western Australia, this is adjacent to the Northern Territory, this is adjacent to the Queensland, and this is also adjacent to the New South Wales and Victoria. So we take this South Australia because which has the more constraint over there. We have converted the into a graph, right? So SA is nothing but Southern Australia. So which has the adjacent of Western Australia, adjacent of Northern Territory, adjacent of Queensland, adjacent of New South Wales, adjacent of Victoria, right? So this graph represents, the edges represents the corresponding adjacent region, right? And finally this is your Tasmania, right? So this is separate. So this has been given in the separate node, right? So here we will see about the backtracking, right? So where about when we talk about the constraint satisfaction problem in the local search. So already we discussed about the local search in hill climbing, right? So where hill climbing find out the local maxima, right? And still it faces some of the problems, but still it gives the solution. And this type of local search is going to be based on the heuristic value, right? Because the heuristic is one kind of uninformed search, right? But to overcome that problem, we use the local search with the constraint satisfaction problem and backtracking mechanism. So when we talk about the constraint satisfaction problem in the map coloring, we can backtrack the solution when the stages knows that further no solution is being derived, right? So when we find it, suppose let us take this, the map coloring, right? So where, as I told you, for the Western Australia, you can use a red either or a green or a blue. So these are the possibilities. So all the possibility values being derived, and make sure that whatever values has a constraint over there, right? So that is going to be satisfied, it is going to follow. So if you found if any further solution cannot be derived, then you have to stop at that stage and you have to backtrack it. Suppose if you see next for this solution as red is filled, the next two adjacent nodes can be filled with green either, or we can fill with blue. Suppose if I fill with the green, then what is the next node to be have is either red or it can be a blue, right? So now here to this South Australia, which has more constraint because this is adjacent for all. Now at this stage what happens, I have filled all the three colors, all the three domain values has been filled. Now what is the value of this I can be filled, right? No color is left. Yes, so if you found a stage of where you can derive the further solution, then you have to backtrack to the previous step, right? So that is where the backtracking it. I hope you already learned about the backtracking in DA subject, right? So where we will see about n-queen problem also, right? So this is where the backtracking is. Here we'll discuss about how to fill the values, right, based upon the assignment, that is the legal assignment, and one more is your complete assignment, right? So what is the minimum remaining values, right? So you have to consider, you have to choose the variable which is going to have the fewest legal values, because that is where you can fill the values easily. When you find the value which has more constraint, then that is very difficult to fill it, right? So you have, this is being called as most constraint variable or going to fail first. So this is also based on the heuristic value only, right? And this is going to pick up the most likely values, right? So which will not lead to the failure soon, right? So in that such a way you have to choose the value. So that is why it is named as minimum remaining values, right? So here if you see, first if I say red, right, so this has only the adjacent of these two nodes, right? So if I take next to this is going to have adjacent of these two, right? Next if I take this this has the adjacent of more, right? So this has the more constraint. But if you observe here, red and green is filled, we can fill with the remaining color, which is blue. So when you started filling the value with the fewest legal values, then for the more constraint value, it is easy to fill the color, right? So that is where you have to follow the minimum remaining values. And next is about the degree of heuristic. What is degree of heuristic? Is talking about you have to choose the most constraint on the remaining variables, right? So which is most constraint among this? We know that South Australia is most constraint. So from the most constraint, right? So you can choose first most constraint, which is South Australia, to be filled first, right? So if you fill that, then you can fill the rest of the adjacent value, right? So this is called as degree of heuristic. We know that what is heuristic value, right? So this is a degree of heuristic. And next is about the least constraint value. So based on the, we can choose one which has the fewest value in the remaining variables, right? So if I filled with red, right? So red is going to be filled in Western Australia. The Northern Territory is going to have a possibility of green and blue, right? So where it is going to be a partial assignment, right? So this can be either blue or can be either green also, right? So we have to check whether it satisfies with the legal constraint, right? It could be the partial assignment also, but still we have to fill the rest of the least constraint value, right? So therefore here the heuristic value prefers can be a blue or a green, right? So what are the benefits of CSP? Is first is it is a natural way of representation for a wider problem. If you know about the problem, we can derive with the variable, we can define the domain values, and we can assign values for that and easily find the solution based on the constraint, right? And the CSP solvers can be faster than the state space search. You know how to draw the state space search. We have to derive all the possible solution, and finally we have to find what is the optimal solution. But that is not the case in the constraint satisfaction problem. If it is, unless it is a legal assignment values, we won't go further for assigning it, right? That is one advantage. And many problems which is going to be intractable for the state space search, the CSP can help us to find the solution, right? So we have some problems of CSP.